So today we have our seventh talk, which is called the Tropical Sandpile or Tropical Sandpile model. So probably it's going to be one of the soft talks. So I will not prove anything today. I hesitated if I prove some hard results that we need for the establishing of the tropicals of the scaling limit convergence theorem. But I decided not to. Let's make it soft. So let omega be an admissible domain, and I don't write where on purpose. So let's pretend we are in any dimensions for the moment. And a state of the tropical sandpile model on omega is a pair of P and F, where P is a finite subset of the interior, and F is an omega tropical series. And a state is called stable if F is not smooth at all points of this set P. So meaning that like you can think that the hypersurface, or in two dimensions the tropical curve, which is defined by this series, passes through the collection of points. And today we'll be discussing what does it mean to relax a state, to stabilize it, to come from an arbitrary state to a stable state. Okay, so to do that, we need some technical preparation. So for an omega tropical series given by...
Just a little comment. Just
Yeah.
a little comment on the previous one. Just for categorical, silly reasons, it would be allowed for me to say it's called stable if F is not linear at all points of P.
Yes.
Is it
it's
correct?
exactly the same thing.
We don't really need to go to the smooth category. It's just a piecewise linear category.
Yeah, but that's you know, one of the ways to express the same thing. So not linear, yes. Or the plot of F breaks at all points of P. So yeah.
No, I understand. It's just a little change on language to remain in a much smaller category of objects all the time.
Sure, of course. Yeah, you're probably right. It's more aesthetically correct. But anyway, it's the same thing. So yeah, pay attention to this small slide because it's crucial. So when we write an omega tropical series in terms of an infimum of a tropical monomial, where AV is a coefficient, and then this plus is the product, tropical product, and that times V is like Z to the power of V. So we say that this form is canonical if all AV are chosen as small f as possible. So sometimes some coefficients, some monomials in this series expression doesn't contribute at all. And so we actually force them to contribute at least somewhere by saying that the corresponding coefficient are chosen as small as possible. So let's see a concrete example. The most silly and the most fundamental omega tropical series is just identical 0. And when you write it like this, O omega of Z equals to 0, it is not a canonical form, because you don't see all the possible monomials contributing there. The canonical form is what is written below. You take not the minimum, sorry, the infimum. You take the infimum over all powers or overall integer vectors, which are can happen of CV plus Z times V, where CV is chosen as the infimum minus infimum of this scalar product. So what happens is that we introduce every possible tropical monomial which contributes somewhere at the boundary of our domain. Do you understand so far?
This example is surprisingly confusing to me. Let me talk very quickly about another example and tell me if I'm saying something correct or not. Take the circle with this famous analytical tropical.
That's exactly the next slide. Let's see.
Yeah. Yeah.
So
okay.
that famous thing defining tropical caustic is exactly the same thing as for the zero, but you omit zero. You omit the zero term.
Yeah. Kind of makes sense. Surprisingly, the previous example is more confusing to me. I have to think more about it.
So let me show you how it looks like in one dimensions. In a one dimension, let's say you have an interval, and so you have this zero term. Zero term is just flat horizontal line.
Yeah.
And then what you do, you ask that there are all other monomials which look like this, which contribute nearest the boundary. In principle, it can be different. It can be a higher value of this coefficient, but then it wouldn't
But we don't know.
contribute. So we really want every coefficient to contribute somewhere.
Yeah.
Does it?
Yeah. Is there a now that you mentioned this in the in classical geometry, not tropical, is there an analog of this canonical form?
I'm afraid not, because really everything contributes. In the classical,
Yeah. That's why it's so confusing, because there is no classical counterpart.
Yeah, but this technicality becomes a feature in what follows. So with that, really, we want to write the series for the moment in the canonical forms. And in this, actually, in this famous series, or the one we dedicated so much attention, f omega, when you write it like this, and again I write minimum, I do it wrong. You should write infimum. This series is not canonically written, at least when omega is a compact domain. Why? Because actually the zero term is missing, so you should introduce it. So in terms of this example with the circle and this pyramid, whatever, this thing, you should introduce the constant term, and the constant term will contribute exactly along the maximum.
The constant term with value maximum.
Yes, and it will contribute exactly at this maximality locus.
That's right.
And yeah. So now we use these canonical forms to define the grain operator. So now I propose to call it once and forever grain operator, because it's GP. For other silly reason, we've chosen this name with Nikita. But I think G might very well correspond to the grain, and I'll tell in a few minutes why it's related to grains in sandpiles. So anyway, this operator GP for P in the interior of the domain acts on the space of omega tropical series in the following way. If your tropical series is not smooth, or if you like not linear at this point P, then the operator does nothing. And otherwise, if your series is smooth or linear, at this point P, then GPF is the result of incrementing or augmentation of a single coefficient in the canonical form of this F, so that GPF is not smooth at P. So I'll show a couple of examples, but really, so GP.
Let me ask a question. This is, of course, I know this story, of course. Nevertheless, those two totally characterizes GP just by saying that we add a single coefficient, making it not smooth. Does it
Exactly.
totally characterizes what we do?
Yes, if you include this requirement about be using the canonical form.
Okay, this is very interesting. That just by saying canonical form and by latent smoothness, then it totally characterizes the value of what you are putting there.
Yes, yes. So
That is a kind of a way to very efficiently encode this minimax principle, I suppose.
yeah, but there is another definition that we were using previously, which I find a little bit confusing, which is kind of universal definition as as an operator which extremizes the property, or like the pointwise minimum of all um, omega tropical
That's right.
series which are greater than f and which are not smooth at p. But this is very
That's right.
inexplicit, so it doesn't tell you how to compute it. And what I say now is very explicit, and that's what you see in the following slide. So in this second case, where f is not linear at p, you write it in the canonical form, and somewhere in the neighborhood of this point P, it's linear. So it's this AW plus Z dot W. And so what you do, you define GPF again as an infimum with new coefficients B, which are actually not new for V not equal to W, and BW is the following formula. So, and if you contemplate a little bit, this formula is derived by the condition that you want your GPF to be not smooth at P, not linear at P. So that's how you should choose your coefficient BW to be sure that apart from this W term, there will be some other term playing the role, contributing at this P. That's a easy thing. I don't want to explain it more, but that's an explicit
But it's very
formula.
nice.
Yeah. Okay. So that's some geometric picture for how it looks like. So geometrically, this GP at the level of what the tropical series defines, it just shrinks the face where P belongs. So and you should imagine that this dashed line is the boundary of the face, and then depending on the position of the point P, you see different results.
But it's always, but even, for example, in the second, there is these 4 pictures, and then in the second one, you get a nodal singularity, right?
Yes.
And every other, I mean, the first and the third are smooth.
Yes.
And the second and the fourth are nodal.
No, the last one is even worse.
Yeah, it's worse. That's right. It's worse than nodal.
Mm-hmm.
But yeah, this intrigues me a little bit because haven't we said that the singularities couldn't get too bad as we travel in the modular space?
Yes, exactly. When I told that they can get worse than simple nodes, but only at the very end.
Oh, I forgot that. Okay, that's right.
Yeah.
Yeah.
And yeah, below you see Newton polygons. In this series of talks, we didn't talk much about Newton polygons, but actually to understand tropical geometry, it's something very useful. So these tropical curves, they are dual pictures to the subdivisions of Newton polygons. Some other time, maybe we would talk in much more detail about tropical geometry, but for now, it's not that necessary. And yeah, just to comment for those who noted that because we have this minimum as the tropical sum and not the maximum, we should think that these dual Newton polygons are reversed. So you see in the last picture there is -1, -1. In the max notation, that would be 1, 1. but that's really some minor technicality. Anyway, so a little bit more about these GP operators. So for example, if you apply it to this zero tropical series, then it will be what we've seen in the previous talk, the minimum of f omega of z and f omega of p. And this was exactly what is the scaling limit for toppling functions when we drop a single point.
Yeah, that's right. That's right. So this is the first connection with the scaling limits.
Yeah. And more generally, so from this geometric perspective, if P belongs to some phase phi of the corner locus or of this hypersurface or tropical curve defined by this tropical series G, then you can think of applying GP to this tropical series G as adding what you see above, GP of the zero, but on the phase phi, where you think that you extend this GP of phi outside of phi by zero, because formally it's a function on phi.
Yeah.
Okay.
Yeah.
So that's very explicit. And yeah, just one more picture, one more example. So what happens? You see already this truncated pyramid on the left, and we add a grain somewhere here. And so what happens? We in pink I highlighted the face. And in this phase, you basically draw the corresponding caustic curve, and you erase the boundary. So that's how you translate the what I was telling on the previous slide about adding this tropical series of the phase. Translates like this. So actually, you don't erase the boundary, but you decrease the weight of edges along the boundary by 1. And if those were having weight 1, it means erase. Okay, and from the Sandpile perspective, GP is the following operator. You add a grain at P, you relax, and you remove the grain. Okay?
Yeah.
And important thing to understand what's going on is that for two different points, P and Q, GP and GQ are not commuting. So you break commutativity.
Yeah, but just a psychological remark is that the GP Sandpile is two different GPs, strictly speaking. One is the scaling limit of the other, I guess.
That's why I put this quotient marks.
Quotation, scare quotes.
Yes,
this is scare quotes.
Yeah, because it means that after scaling limit.
But what I wanted to say is that just for psychological, historical purposes, the Sandpile GP was discovered before the tropical GP. Motivated the tropical
I'm
GP.
not that sure. So I think in 90s there was something in string theory called breathing mode or whatever in the works of Laffa. And it was about exactly same operator of contracting the faces of the webs, which are kind of strings. So I know very little about that. I just remember that it might happen that this tropical side, even before tropical geometry, was known to physicists.
Yeah, that's possible. But in your own experience, probably the GP Tropical Sandpile came before and motivated the GP Tropical from this perspective.
From I think kind of the same time, because we were doing experiments on the computer, and usually we were working in the mode when those sandpile configurations look really like tropical curves. So yeah, and that was so maybe first we discovered waves, and then we understood that waves acts in a good way on solitons, and we understood that waves contract faces, and then we came to the idea of integrating many waves to something which shrinks face in order to for the boundary of it to pass through the point. So something like that.
Excellent, excellent.
Okay. Now more of this analogy. So what corresponds to the maximal stable state in the usual sandpile model, so all three, is now interpreted as the empty set of points and the zero tropical series. And what we would like to understand from the sandpile perspective is perturbation of this maximal stable state at some number of points. And here in the tropical level, it's just done by introducing some collection of points where we would like to have our curve to pass. So this state P0 is our state that we want to relax, but so far I didn't speak about the relaxation, and so now I want to tell what is the relaxation, at least of this state. So you start with this initial state, 0, and then you go for F1. So you apply GP of some point, K1, then you apply GP K2, and etc. So you go forever. And it's called a relaxation. And obviously there are many relaxations, and that's the main theorem. I thought of proving it today. It's not awfully hard, but still I decided let's make it soft. Yeah, so that if in this relaxation each point is taken infinitely many times, so we don't forget about second point, we do it time and again, or third point, etc. Then this sequence of omega tropical series converges to the series Fp omega, to the function at least, Fp omega, and it converges uniformly, and Fp omega depends only on the chosen points and the domain omega, and it doesn't depend on a particular relaxation. So if in this relaxation every point appears infinitely many of the time. Now I think I want to tell you what is this limit, Fp omega. So first of all, it's an omega tropical series. It is not smooth at every point of P. In other words, P Fp omega is a stable state. And it's the pointwise minimum of all functions satisfying the first two properties. And this you can take as a definition. So you can prove that there exists unique Fp omega satisfying these properties, and this Fp omega will be appearing as the limit of this relaxation process. And the last condition about the pointwise minimum should remind you the least action principle in sandpiles. Okay? Yeah. And going to the next talk, so we will need this. We'll need this relaxation process and the final or eventual configuration, this Fp omega, and we will see that it will be the scaling limit for the corresponding sandpile relaxation for the toppling function of the perturbation at several points. Yeah. Okay. So this is the picture from our paper. So with many authors, including some of the guys present here. So Ernest, Nikita, and me. Yeah. And so that's what happens when you add a lot of points on a square. And to be completely honest, I've taken the picture which is at the sandpile level, but here is the curve is kind of visible. And what's important about this curve, at least in the middle, it's kind of homogeneous. It's made of some pretty coherent matter, if you like. It's some kind of perturbation of a grid, of the standard square grids, and so the slopes of the edges you'll see in the middle are only of 4 types. So occasionally there might be a higher slope, but usually there is only horizontal, vertical, and 2 diagonals. And I think it's not proven so far. It's something I think very much provable with some probability theory.
Very nice. Here, nevertheless, one should mention that Nikita and Juliet have a paper on the statistics of.
Yeah, that's actually
that's
a very nice paper. It's so although it's simple, it finds some, for example, correlations or identities between the coefficients of this tropical polynomial. Also, it proves that if you remove those points from the curve, you get a tree. This is also some very nice result, and I think it might be very useful, at least in some instances, about what I'll speak later. But yes, this is a nice paper, and I'll put it to the caption on YouTube.
Here I have a comment that somehow if you have a collection of points on a tropical curve, such that if you remove it, you obtain a tree, it's called a break divisor. And that's exactly the divisor of degree G, right? So if you have a curve of genus G, then somehow it's a theorem of Mikhalkin and Zharkov that in every divisor of degree G in each linear system, there is a unique representative, which is kind of this of this break divisor type. I don't know how it can be useful, but somehow this is so kind of naturally we obtain here divisors of degree G on curves of genus G.
That's right, and this is very reminiscent of the original definition of homology by Riemann. That was the way he thought about homology of Riemann surfaces.
Okay. Well, this is one of the directions I think we should explore.
Fantastic.
So one more comment that there is another minimization problem that this curve solves. At some moment, Eliashberg proposed to call it tropical Steiner problem, because in the case when the domain is a compact Q polygon, the corresponding curve solves the minimization of the symplectic area in the class of curves that pass through the given collection of points. However, this minimization doesn't define the curve. So if the curve is not rigid, there might be many solutions, although belonging to the same deformation class. And to tell just a few words about how you deduce this minimization, it follows from the action minimization and the fact that symplectic area of this curve can be computed in terms of the symplectic area of the boundary, but you need to weight each edge on the boundary with an integer, which is the quasi-degree. So I'm not going there. Just show you in this precise picture what quasi-degree could mean. So on the left, each weight of edge is 1, and it says that the slope of the corresponding tropical polynomial is minimal. And on the right, for the edge above, it's 2. And you get the idea of what is quasi-degree, but I put this picture for the other purpose. So I wanted to tell you that this FP omega is not a continuous operator. Namely, if you slightly perturb the configuration of points, sometimes the solution jumps drastically. And that's what you see for going from left to the right. And so...
But is there an upper semi-continuity property here?
Nikita, I'm not sure. I think it's confusing. Probably not, because yeah, it's going to jump in whatever direction you go. So you have some discriminant, and yeah.
I think it's upper. It's upper semi-continuity, lower semi-continuity.
Yeah, I think it's upper semi-continuous, but yeah, maybe lower semi-continuous.
What I mean is,
but it's one of the two.
If you have a sequence of points, I mean, there's a sequence of collection of points, construct functions for them, then in the limit, the function for the limiting collection of points is less or equal than the limit of functions.
Mm.
I don't remember which is upper semi-continuity or lower semi-continuity, but it's one of them.
Mm.
But if it is the case, then it connects it to some beautiful invariants, both in singularity theory and in knot theory. But we should talk about that later.
Yes. So what's also important that when you do these small perturbations, the number of steps in the relaxation can explode. So far, actually, I didn't tell that in all examples is going to be finite. So, for example, if your domain is a lattice polygon and your points are lattice points, then this relaxation is always finite. But it can be really long, already for 2 points. And that's the main conjecture. And I've heard Nikita's opinion once, not so long ago, that he thinks that maybe in general it's false. I suggest to tell that tropical sandpile model is non-Zeno. Zeno, as the Greek philosopher who does porisms, and this is a terminology in some dynamical systems, telling that your process doesn't go forever. So Zeno property is phenomenon is something which is in principle finite, but it takes infinitely many tiny steps that get smaller and smaller. That's what you have in this arrow paradox and this Achilles and Tortugas. The process is in principle finite if you look at the totality, but it's done in infinitude of tiny little steps. And the conjecture is it's not true, that actually these relaxations, they are always finite. So they terminate after some finite number of steps. Does it make sense?
Yeah, but what I'm confused about is what are the hypotheses, because this would sound as a general statement even for more general sandpiles. So I'm confused about the hypotheses here that make this not obvious.
It's not obvious at all. Okay. So in what follows, for example, in the proof, we don't use that this process actually terminates.
Misha, maybe you can remind what is the relaxation here, because here relaxation is not like application of steps. So here there is a result of relaxation which is just defined as a pointwise minimal function, blah blah blah. And then there's a theorem which is not trivial.
Yeah. Now I understand. The problem is that we're talking about slightly different things. You are talking about the tropical geometry side of the story, not the sandpile side. Yeah. In the tropical geometry side of the story, we don't know. Of course, there we don't know because we have all these just GPs that we have to apply many, many, many times, and we don't know that it ends. because it's the scaling limit.
Yes.
But at a finite Sandpile, we know it ends.
Yes, so that's the thing. That's that we don't have scales, and in principle, this is some arithmetic stuff. So it's like
That's right.
doing Euclid's algorithm for a rational and irrational number. It can take forever, although the steps get smaller.
That's right. That's right. That's right. That's right. Now it sounds highly non-obvious and even sounds vaguely false, but but I don't know. I don't know.
For example, that's
So
what I'm proving in 1D.
Yeah. In 1D you prove this. In 1D you prove this. That's right.
And it's not obvious if it's true in 2D. So there might be, in principle, the configurations that are not stabilizable.
Do we have an example in 2 dimensions? Do we have an example in 2 dimensions? I suppose we do, of one that actually terminates. I suppose
Yeah,
we
yeah,
do.
of course. Like all examples, for example, take a lattice polygon and as your domain, and take your points as lattice points. Then it's obviously something finite, because each step will be an integer increase of the coefficient, and you know that the process is bounded.
But even if we have the circle and just the center point, this is not obvious at all, is it?
No. For 1 point, your relaxation terminates after exactly 1 step. You do just one GP, and it's stable.
Yeah, the problem is the problem is transcendentality between the different points, I guess.
Yes, that's transcendentality between points and transcendentality between points and coefficients.
Yeah, I see. And you still believe that even with bad transcendentality situation, it will terminate?
Yes, I think, but that's really cool. You see, this FP omega operator, in a sense, it's a limit of applying GPs. But since the number of steps you need to take can be, it's not finite, but it's finite, but it can be different. The limit is not, it loses continuity. If, yeah. Anyway, so in the last couple of slides, I'll tell just one strategy that we had for proving this, and to add to the eclecticity of the topic. So the suggestion was to lift the GP operators to algebraic geometry. And here the particular lift is in characteristic 2. But I think it can be done in all positive characteristic. I'm very skeptical it can be done in a 0 characteristic. I think there are topological abstractions for constructing analogs of GP. At least if you throw in some more requirements like the lattice invariance. But anyway, let's do it in characteristic 2. So in characteristic 2, you take some non-Archimedean field, K, with real valued valuation. And I recall the tropicalization of a polynomial over this field is just taking this minimum of where the coefficient becomes the evaluation of AV. And we want to lift GP with respect to the tropicalization. And so this is the formula which was found in 2 steps. So first I found some wrong formula, and then Nikita found a correct variation of that formula. So this is not perfect, but still it works. Why not perfect? Because you need to specify 2 cases, but it's similar to what you did to GP. So when your function, even your polynomial is not is 0, so at P, namely the defining curve or hypersurface passes through P, you do nothing. Otherwise, you do the following. So you take FZ and you add the following crazy thing. And here we heavily use that characteristic x2, and there is also one extra assumption that square root is at all possible, so meaning that Frobenius automorphism is invertible. But the proposition or theorem is that this SP operator is exactly the lift of GP operator, so it shrinks the phase. And then the refined conjecture might be that the dynamic defined by SP for different points, for several points, converges. So same statement, convergence, but convergence at this non-Archimedean level would mean stabilization at the level of tropicalizations.
Very nice, very nice. Now this formula seems a bit too magical, you know?
Yeah. But like cool thing, you see it preserves, for example, the Newton polyhedron, right? So
I'll have to think about it.
But it really acts on the linear space. Also, there is some technicality that we were defining GPs for omega tropical polynomials. Now it's for just usual tropical polynomials, but this is minor. And this is why I say also there should be some condition of Newton polygon being big enough. Newton polyhedron being big enough, because, for example, if you take linear equation and 3 generic points, then well, even if you can move this line to pass through one point, then to the other, then to the third, it will never pass through all 3. So for this reason, Newton polyhedron should be sufficiently big with respect to the number of points. But this is a statement in non-Archimedean dynamics, and I think it might be easier to to do it like in formal analytic manner to prove that the following operator converges, and yeah, that was a dream, and we never met anyone who was too specialized in this kind of stuff to give an advice, but still I think it might be a nice thing to do.
Yeah.
Okay. Questions?
No, everything is confusing enough. It's fine.
Okay. So next time we will be proving the convergence in the scaling limit theorems for several points. I suggest you to watch the previous video about 1 point. And I don't know how long it will take, but I hope to do it in one single talk. And yeah, thank you.
Fantastic. Thank you. Very nice talk.